Hello. Now let us look at the assignment we have given last week. We had three assignments. The first one is a draw and run ORCA calculation and compare the HOMO and LUMO of ethylene and compare with formaldehyde. The second one is to draw and calculate the dipole moment of TNT, and the third one is a draw and visualize the HOMO and LUMO and ferrocene. So let us start one by one. Let us start with the simplest one, that is ethylene. So the first step is to go and start Avogadro, which will help us to draw the structure. I am going to show it using Avogadro, but you can use the other two GUIs also, and I will encourage you to actually use the other two GUIs. My Avogadro is open and I want to draw ethylene, so that I have to draw the bond order to be 2. Optimize the geometry a little bit so the structure becomes a little bit easier, and I want to generate ORCA input file. Everything is fine. Don't forget to give the large print. The spelling mistake. So it's ethylene, and you can save the input file, and you can run from here. ORCA ethylene dot INP ethylene dot out. Spelling mistake. Now it's running. And remember, when it runs, it generates a lot of temporary files. So now the calculation is done. Let us try to open Chemcraft. Let's try the Chemcraft. So it's ethylene.output file I am going to open. And of course, I want to go to orbitals. Let us see the HOMO and LUMO, what we are most interested in. Let us see the ISO surface. So let us try to make the view a little bit better. So let's see the HOMO. Now you can see the HOMO that it's a classic case of a pi bonding orbital. So where the bonding orbital, the node is along the bonding axis, the principal axis, and that's why it's a pi bonding orbital. If I go to the LUMO, you see that the node is actually perpendicular to the bonding axis. So, and there are two nodes. This is That's why this is an anti-bonding orbital. So the bonding and anti-bonding characters are very clear here, and this looks like a classical pi bond. Whereas if I want to go to the example of formaldehyde, and I can go to the tools, render orbitals, again I render the HOMO and LUMO. So see, there is a distinct difference between the character of the HOMO and LUMO of formaldehyde and ethylene, although they are isoelectronic. The reason is that because here there is a mixing between the carbon orbital and oxygen orbital, which are not of equal energy, so they do not give you such well behaved orbitals as is observed in the case of ethylene. So just remember that sigma and pi bonds are generally properties of linear molecules. For nonlinear molecule, they may not be very clear to look at. So at most they are sigma type or pi type orbital. So this is how the antibonding orbital in this case looks like. So this was the case of ethylene and formaldehyde. So by looking at least for the ethylene, you can easily say which one is the HOMO and which one is the LUMO by looking at the orbitals, basically looking at the orbital which is where is the node. By looking at that, you can always should be able to tell it which one is the bonding, which one is the anti-bonding. If I want to look at it again, it's orbitals, render molecular orbitals. So for the bonding orbital, the node is along the bond axis. For the anti-bonding orbital, node is perpendicular to the bond axis. So looking at it, you should be able to tell it's a HOMO or LUMO. Let's go to the next example, TNT. You can generate the TNT in multiple ways. Okay, let me go and clear this one. You can generate it in multiple ways. I can generate in one way, you can generate in another way. So it depends upon you. Here what I am going to do is that I am going to generate it from the Avogadro. You can try by using 2D utility of Chimera-X, and then we can compare our nodes. So the first thing I will do is that I will go to the build. Let me start show it from the beginning. I will go to the build, I will go to the insert, and from the insert you can actually insert custom fragments, and custom fragments I will go to aromatics. From the aromatics I will come down and go to benzene. So now I have benzene and I want to rotate it. So let us select this one. Now let me pick TNT. So to do that, the first thing I have to do is that I have to take the first hydrogen I have to replace by a methyl, and the bond order should be single. So let me first put the methyl group. Now I will replace that hydrogen by nitrogen one by one, and of course the bond order here will be single. So let me replace this one, this one, this one. Oh, this one I did not do correctly, so I do undo. Now the next thing I have to do is to replace the nitrogen by oxygen. We have to make sure that I don't adjust the hydrogen for the oxygen because they need to be double bonded. So now my TNT structure is almost there. I will go to the extension, I will optimize the geometry, and I can get to this TNT structure. I will do the same thing. I will save it as a TNT input file. maybe I should have made a separate folder. So week 2, let me make a new folder and let me name this folder as assignment. And no, I don't, I can save it as an XYZ file just to be on the safer side. TNT, and let me try to make an Orca input file. Okay, so my Avogadro has crashed, which is good because we have saved it. Now I can make my input file. Generate Orca input file, everything is good. I am not going to see the molecular orbital, so I can just generate as TNT and save it in the assignment folder. And now I go to this assignment folder, open the terminal here, increase the front a little bit, so it's Orca TNT dot inp. Orca spelling is wrong. This calculation may take some time. So as the calculation run, let me try to make the ferrocene input file. This is like a parallel processing. So for ferrocene input file, again you can do it in many ways. So I am going to use the simplest of that thing. I will go to the Chemcraft, I go to the edit option, and from the edit option, there are many of these options you can see. Select all, flexible, expand selection, reverse selection, basic editor option like this. So from the edit option, I have to go to the add fragments, and here you can find many of these options. So I will go to this coordination, metal ligands, sandwiches. In the sandwiches, I will see the option ferrocene. And there are two configurations, ferrocene staggered and eclipsed. You have created it in the group theory. So we are going to use the ferrocene eclipse, which has a D5H symmetry, and this is how it will look like. So once I am done, I will save this one as an XYZ file, and I am going to use the simple XYZ format, not the atom type as number, but atom type as character. And this I am going to save as ferrocene. Our calculation is still going on. So after my TNT job is finished, let me try to open it. I need to go to my NPTEL week 2, I go to my assignments, and if I open my TNT output file, I can see where my dipole moments are located, and no doubt that it is pointed towards the CH3 one, because we know this will lead to separation of charge between the nitrate and the methyl group, and this is where the dipole moment will be localized at. Next we go to the option of the ferrocene job. Let us first prepare the ferrocene input file. So, to do the ferrocene input file, what we will do is that we will, let me clear the previous one. I go to the edit option and I go to the option add fragments. I am not saying that this is the best option to generate the geometry, but you can also generate it in other ways, but this is the way I did it. So, I will go to the option of coordination, sandwiches, and I take the ferrocene eclipsed. After I get it, I save it as a structure as an XYZ, simple XYZ format, atoms type as character, and I save it as this one. Now, if I go and try to open it, assignment, and I try to open this one with Avogadro, and it says that it cannot, it's reading the molecular file failed, so it cannot open it. And the reason is that when you save it with Chemcraft, what happens is that it fails to save the number of atoms, and the format of the XYZ file is in such a way that it first need to contain the number of atoms and then one line space and then the atomic coordinates. So, for the now ferrocene, the number of atoms we know is 21. So, what you have to do is that you have to put the 21 by hand, put one space and save it. This should now be open in the. So, now you see it's has the proper XYZ file. Do not get perturbed by the one bond of the ferrocene with this one. This is just a representation. Remember, while saving it in the Chemcraft, you have to manually edit it to put the number of atoms. Now, let us try to submit the job. I generate the Orca input file. I have to put the large print option. And I can save it. So, I run the calculation, and this calculation may take a slightly more time. So, once you are done with the calculation, what you can do is that I can clear this structure, and I can went to open, and I can open the output file. So, once you come to the output file, I can go to the orbital and render molecular orbital. So, I have 48. So, basically I will visualize HOMO, HOMO minus 1, HOMO minus 2, maybe up to HOMO minus 1. This should be fine, and as well as LUMO. So, this will do the rendering. Once your renderings are done, let me start seeing from the LUMO. See the picture, it has a ring around the iron and some molecular orbital is also in the ring, but it mostly looks like a dz square orbital of the iron. And then there are other orbitals, it has very nice shapes, and if you are interested why these shapes looks like this is what is called a symmetry adapted linear combination. You should consult a group theory book why the ferrocene orbital looks like this. We are not going to go into that discussion, but this is how you can draw molecules and can generate orbitals and try to get chemical conclusions out of it.